Hello, and welcome to this lecture, number 2, Normal Process Scheduling on the module of scheduling. We covered Linux scheduling in the first lecture, and now we will get specifically into what normal processes use for scheduling. Now, the normal process scheduler is the completely fair scheduler. And you can read up about the completely fair scheduler. It has been around since about 2007 with 2.6. One of those versions, and is by default the normal process scheduling algorithm or the scheduler behind it. Now, this scheduler provides fair execution time for all tasks based on a weighted load model. And the term is fair because it takes input into what your load should be, and it gives you fair scheduling according to that. In the mix, it'll ensure that all tasks get scheduling time on the processor. Now, it uses as a input to itself a nice value. So processes have nice values, and it uses the nice value to derive a load weight value. Ultimately, the completely fair scheduler makes decisions on the load weight value comparison between processes to tell who gets more, who gets less. And because the nice value exists for processes already, it uses the nice value to determine how much of the process time to give for a certain task. Now, it keeps control by measuring the CPU execution time that a task has taken. And the measurement happens in nanoseconds granularity. So it is pretty detailed in the level of measurement that's happening. And then the way it uses the load value is that it uses and calculates a virtual runtime. Because between different load values and execution times of the CPU, how do you compare different tasks? Who gets the CPU? So there is another calculation done so that you can come up with a simple number, and that happens to be the virtual runtime. Now, the virtual runtime is the execution time, but it is weighted by the load weight of the process so that you can compare different tasks that are running together. It does schedule the task with the lowest virtual runtime. And the logic behind it is that if you have the lowest virtual runtime, it is fair that you get scheduling so that you can increase the virtual runtime. And you get fairness with regards to the other tasks, which obviously have higher virtual runtime than you have. So that's the basis of how CFS works. Now, let's look at a diagram here and see how the task is connected to this scheduler. Now, there is an entity called a schedule entity, a struct schedule entity, and so there is a schedule entity created for a task, and the task points to that schedule entity. Now, within that, you will have the load weight of the task. You will also have, we just talked about the V runtime, which is the virtual runtime of the task, and the full execution runtime. And I'm talking about a few fields that are important among the others that are here. And the sum of exec runtime is actually the runtime in nanoseconds that it actually took CPU time. So this is an absolute measurement. The V runtime is that balanced measurement that uses the load of the process to tell how do you compare different tasks on runtime. And the formula is that you take the sum exec runtime and then you multiply it by the nice zero weight and divide it by the actual task load weight. So you compare everything to the load weight of a nice zero process. And the reason for that probably is nice zero is the default. The default process is given a nice value of 0, and it has a nice task load of 1024. So 1024 divided by the actual task load weight provides that ratio, which is then multiplied with the actual execution time that the process has received. Now, for nice equals 0, this means that the task load weight will also be 1024. So for a nice value of 0, that special case, the V runtime is actually exactly equal to the sum of the exec runtime. It's equal to the actual time that you ran on the CPU. Now, How does this scheduling and V runtime calculation work and be effective? The way the scheduler works is it keeps a red-black tree structure of V runtimes. And of all the sketch entities that will be available, because we just showed that a task has a sketch entity, so if you have n number of tasks, you will have n number of sketch entities, and this is for one CPU. So there is a red-black tree where all these V runtimes are kept such that it's a balanced tree, and they're kept such that it's efficient to read and find out who the process or the task is with the lowest V runtime. And the leftmost task will be the one in this structure that will actually have the lowest V runtime. So there will be a direct pointer to the leftmost task in the scheduler, and it always gets the lowest V runtime task to run from that. The rightmost task would be the one with the highest V runtime. So technically, it has received the highest time on the CPU. And every value in between will be somewhere in between. And constantly, as we talk about this kernel, the CPU accounting, as all that accounting is happening and these values change, so does the tree change the nodes and moves things around. But it helps as a data structure to efficiently find out which task has had the lowest V runtime and therefore should be scheduled next by the CFS scheduler. Now, let us go back to what we looked at in the previous lecture on scheduling. Every CPU has a run queue. So CPU 0 will have a run queue for itself. And within that run queue, it will have run queues by the real-time scheduling class, and it'll have a run queue for the CFS, the normal scheduling class. So two separate run queues. We are going to talk about the second run queue here for the normal processes, which is using completely fair scheduler, CFS. This one will point internally to the red-black tree with the V runtimes, and you can see from this structure that task 2, which is pointing to V runtime 2, is the leftmost one that'll have the lowest runtime and therefore will be selected to run. So the scheduler actually is maintaining these data structures and finding out the lowest V runtime among all the tasks that need to be run, and is giving the chance and opportunity to that task to run. This is how it accomplishes finding out which task should get the CPU, and it is fair in the allocation of CPU among all tasks based on the load weight that is provided to the task. Now, when we look at the nice value, how does nice value convert to CPU execution time, and whether you will get more or less? So let's look at this in a little bit more detail. So the nice to load weight is the first level of translation that is done because the V runtime is not directly calculated using nice. And then the load weight is then converted to the V runtime in a second step. So if the nice is -20, we said it is the highest priority process in normal processes. And a +19 is the lowest priority with a default of 0. For every nice decrement, there is a formula on how it calculates the load. So for every nice value decrement of 1, the scheduler will give it 1.25 more execution time on the CPU. And there is a table, and on the right I've put that table, and it is roughly 1.25 times, and the math goes a little off here. But ultimately it derives these values on roughly that number. So in the right table, you can see that for 0, you have 1024. Now, if the nice priority decrements by 1 and becomes -1, the load weight will increase to 1277, which is roughly equal to 1024 multiplied by 1.25. If you now further decrement this by -1 again, you will again have the value multiplied, the previous -1 value of 1277 multiplied by 1.25, giving you about 1586. On the other hand, if you are going the reverse direction, which is you are incrementing by 1, so from 0 to +1, you will actually divide by 1.25. So your load weight will be 1024 divided by 1.25, giving you about 820, and then the same story goes on in that direction. This leads to the extremes of minus 20 being 88,761 and plus 19 being 15. So you can see, even though we just had like this small 40-point difference here, we created a load weight difference using this 40-point scale of roughly going from the lowest weight of 15 to 88,761 times. So you create that load weight range. And the V runtime is going to be calculated using that load weight. Now let us take a few examples here. And in example 1, you can see nice is 0. V runtime equals the sum of all the CPU execution runtime multiplied by 1024 divided by the load for nice equals 0, which is 1024. So it's exactly the same as the sum exec runtime. Example 2, we decrement the nice, which means we make it a higher priority process. Now the V runtime in this case will multiply it by a factor of 1024 divided by 1277. And that is about 0.8 times the sum exec runtime. So how did it actually give, how is it going to give more time to a nice process with -1? Just look at, we are actually multiplying it by a number that reduces the execution time. So V runtime now is smaller. So this process will be favored more because we just said, right, lower V runtime means you're supposed to get more. Now example 3 is where, let's take the extreme of nice value of -20. Now the execution runtime will be multiplied by 1024 divided by 88,761, which is about 0.011 times the execution time that you already had. Similarly, if you go to the opposite direction, in example 4, we can see the nice value is +1. So it'll start going in the reverse direction. The V runtime will actually show more than the actual CPU time that you had on the process, for the process. So that's how the V runtime is calculated. And these nice to load values are not calculated every time. There is actually a table that exists for all these 40 values. And these are the precise numbers that are used in that table for calculation. So it's pretty much set. These numbers are set and they are coded into the code, and you can look at it in the code if you want to. That's in the sketch.c class. Now let us see, how does this compare on percentage of CPU time when you actually change these load weights. Just take a few examples. So let's take an example when you are running two processes, because one process by itself is great. You got more or less, but you're always looking at time compared to another process. So now let's look at two processes that have an equal weight. So they're both at nice value 0, process 1 and process 2. They both get a weight of 1024. Now the total load on the system is, and you're assuming again that these are all on the same CPU, would be 1024 plus 1024, which is 2048. Each one of these will have 1024 out of the 2048. So the percentage CPU time that each one will get will be 50% each. So this is where equal weight gives you equal CPU time. Now let us take the case where we have three processes and they don't have equal nice values, which means they don't have equal weight. So process 1 has a nice value of 0, and that gives it a weight of 1024. Let's take process 1 or process 2, which actually has a nice value of -1, so you get a weight of 1277, and process 3 with a nice value of +1, which gives it a weight of 820. We do the same formula, we get the total sum of the weights that we have, which is 3121 when you add all these up. And then the percentage CPU time that you will get will be by your weight divided by the total weight of all processes. So process 1 will get about 32.8% being at the default nice value of 0. Process 2 should get more CPU time, and in this calculation you can see that it does. it has a nice value of -1, and it got 40.9% of the CPU time. Process 3 has an increment in nice value, so it has a lower weight, and you can see the result here in this calculation. It'll get 26.3% of the CPU time. All of these processes will be running. VRun time will be used to calculate how much time they get, but this is exactly overall how much CPU time they will get to run. CFS does switching, but we also talked about context switching comes at a cost. So there is a period defined, and that's called a minimum granularity period. So you let a process run, and that time that you provide it to run for a minimum is defined in this variable. So I did a cat on this variable, and you can see that it is 10 milliseconds setting on my server. Now it can be different, and you can see these by looking at the settings that you have, but I do find that it is 10 milliseconds, and I believe that the range generally is between 1 and 10 milliseconds. There is also a concept of a latency period. Now the latency period is really not hard bound, because the latency period is a concept of what is the latency between a process or a task getting scheduled once and then getting scheduled one more time. Well, that depends on all the other tasks that are going to run, and the other tasks may have more priority. So the latency period is a variable, but the scheduling minimum granularity time that you get to define in nanoseconds here is actually going to give you that guaranteed time. So there isn't excessive context switching happening. It is the minimum time slice you get once you are on. So let us now see a few scheduling process examples. And what I've done is I've looked at some of the processes running by default. I've not done anything special. I just look at my server, what's running. Let's look at Poken in a little bit more detail what's happening inside. So I took PID 1194, and I see that it is the audit user audit process, and the parent PID is 1. It's of class TS, so it is a complete part of the CFS scheduling, and the nice value is -4. There is a lot of interesting data that we just talked about the scheduler that is available to you if you look into the proc/pid/sched file. So this file, when you look at it, will show you all the scheduling information related to that process. Now, let us look at the fields that we already recognize now. We can see that sc.vruntime, that is the scheduling entity.vruntime. We talked about it, and you can see the value here. You can see the sum exec runtime. That is the total runtime in nanoseconds that this process actually ran. And then let's go down a little first to look at the load weight. And you can see that the load weight on it is 2501. Now 2501 is based on the derivation that this has a nice value of -4. So when you look at the table, we have -4 should translate into this load weight of 2501. The policy is 0, which is scheduling policy for normal processes. The prio number here is 116. So how do you convert -4 into 116? And the way it gets converted is, now we know that the real-time priority was 0 or 1 to 99. And now there is a combined priority view where these two have been added, the nice system and the scheduling priority for real-time. And now you get a new priority here that goes between 100 and 139. And so -20 becomes 100, and nice equals 0 value becomes 120. And if the nice value is +19, you get 139. So there is a new 100 to 139 range, and it's there such that you can extend sort of the whole priority range between 0 to 139 instead of working with these different ranges. So that's just how you translate the priority value of 116. The 116 really means 120 is nice 0, 116 is 4 less than that, so it is nice -4, which we know about this process. So the other fields that are interesting here are number of migrations. Number of migrations means how many times it actually got migrated from one CPU to another one. Number of switches. Switches means the task is running and you actually switched out of the CPU. And there are two kinds of switches. We discussed this already in scheduling as well. You have voluntary switches and involuntary switches. Voluntary is when you are done, you yield the CPU, you don't need it anymore, you go to sleeping. And involuntary is when you're running and you want the CPU, but somebody else that is higher priority than you gets the CPU, and so you're switched out. It is a good number to see if the involuntary switches is just too high. Just it means that you are being switched out quite a bit on CPU time. So these are numbers that you can see, and now you're able to interpret into this data file. As an example, I just took another one, and it's very similar. You get V runtime, exec runtime, load, waits, switches happening, everything on another process in this case that I did. The interesting thing that I found was just that the whole relationship between the sum exec runtimes and the V runtime. And one thing to note is that the V runtime, because processes, when they migrate between CPUs, they are supposed to sort of be balanced and not just come from one CPU where, you had a certain value of V runtime and then you are a new process and therefore your V runtime happens to be low, and you just grab the CPU, and just because you have an old process that's been running there for a long time, you just calculate their V runtime to be higher, and new processes will that way always get the CPU. So to manage that part and manage how migrations between CPUs do not impact the comparative V runtime between processes, the V runtime, when you have a process, you always add your V runtime to the minimum V runtime of the CPU. And that is how you get the V runtime calculated. So this V runtime, you got to keep that in mind, that the V runtime is actually the V runtime of the process and added to the minimum V runtime that's on that CPU. Otherwise, if you look at this number, the priority is 100, and the V runtime actually, if you look at a 100 priority process, which is minus 20, in nice value should have been smaller than the sum exec runtime, not bigger. And here it is bigger, and that's the reason it is bigger. So it's just to understand it better. Otherwise, it doesn't really change how V runtime is calculated and used in load balancing. Now I'll show you just another couple of tools and that you can use, and in CPU utilization, I started a process with Stress, and Stress is a tool that you can download. You can do an install using yum install or apt-get on Stress. It's available with distributions. So this is a useful utility to put load on the system, and I will use it to generate CPU load. So I do a dash CPU of 4 and give it a timeout, so it'll just time out in 120 seconds and stop. So when I run that process, I can see after that I run a PS command and see the utilization by this Stress process that I ran, and I can see that it's running a master Stress, which spins off 4 child Stress processes, one for each CPU. Or one for each workload on a CPU. And you can see the C column here, which is the actual CPU time, and you can see that 99% is being allocated to each one, and that means they're 99% on each of the 4 CPUs because I'm running a 4 core server. You can also use a mpstat command, and that tells you utilization of CPU across these processors as well. And you get a similar story here. You could see that 0, 1, 2, 3 all have roughly 100% utilization. And that is because the Stress tool just stresses and is always just constantly using CPU. I think it calculates the square root function and just keeps on going. It also gives you the mpstat, a top line, which is CPU all, where it'll average all these individual CPUs. But it is important that you understand that all is good to know, but individual loading of each CPU is also important to know, because a task will always run only on one CPU. So sometimes you can have an imbalance, and the way you find out is by finding out, okay, which CPU is really hot within all of those. So in this case, all of them are, the total is 100% nearly. They're all individually nearly 100%, and it's just showing you what's going on. The other interesting aspect here is just looking at the user percentage, and that means it's all user space utilization, not system. System numbers, if sys was high percentage, you would see that the kernel is taking time for that process. And we will get into some more details around these later on. But right now, I think the columns that are of interest are the user, because you see that the CPU is being used. It's being used by user time by this program. The sys time is actually pretty low, but that is the kernel time to be utilized. On the right side, you can see percentage idle. We talked about the idle process. It is not running because there is actually a real task to run. So idle is at 0 here. Now, we can take another example and say, let's try the same stress. And what we are going to do now is see if we can just increase the nice value and see the results of CPU when we do that. Now, in this case, I started 5 stress tasks and not 4, because even if I raise the priority on 4, they all are on one CPU. Nothing will change because I have a 4-core system. So I added a 5th one just to look at the dynamics change a little. So I'm running 5 CPU worth of load, and then I do a top command just to see the utilization, and I can see actually that here the CPU is showing 85%. Now keep in mind that this was initially the first top command, and one is 85, one is 80, the other one is 88, 79, 78, 77. So there is a rough range, and know that CPU does not divide equally. Just because a processor that's running will be running a process fully, and therefore you deal with migrations between the CPUs of the process, and even if they are equal weight, like in the first one, you do not get an equal distribution unless you look at the values in the long range. They will be equal, but not in the short range that you get from the top command. Then I renice one of these, and renice is a command I can use actually to change the nice value, and I say -5, so I change it to -5 for one of these stress processes. And then I look at it again, and I see that one of the processes actually is now getting more CPU time than the others. So 1290, where I did a renice, and the nice value is -5 now, I can see that it is showing 99.7% of the CPU, and the others are still managing within themselves CPU time. Now, this shows that by giving more or decrementing the nice, I was able to increase the load weight for that one process, and I was getting more CPU time for that. So we have now completed the view of how normal process scheduling works. What are the tunables that we have here? And in the next lecture, we will be looking at group scheduling. How can you actually have multiple processes together be scheduled in one group and get CPU time constrained by those group factors? Okay, thank you.